So that means I will take G being negative. I will often write it minus modulus G less than 0. And that means we just replace F that we remember we defined last time. That was by definition G times density of states at the Fermi surface goes now into minus F, which is, so, and when now F I will define as modulus G times the density of the Fermi surface. And if I put here a scattering length, expression for the G in terms of scattering length, that would be 2 modulus scattering length, S wave, of course, PF divided by pi h bar. And that was our, I remind you, small parameter. So you can, of course, ask me what will be the difference, yeah? Because we have perturbative expansion, and somehow for perturbative expansion, it doesn't really matter whether they have positive or negative small parameter. And indeed, you would be to some extent correct, yeah, because remember, I have an expression for the chemical potential, I have an expression for the effective mass. You just replace the F to minus F, and this would be, okay, the correct, well, almost correct answer for these quantities. The things that will be missing, if you look carefully at the expression for the zero sound, yeah, for the zero sound. Then, of course, for the negative F, you will find out, you can have a look at this expression. For the zero sound, you will find that S, remember that parameter that was specified the difference, so the speed of a zero sound, that would be less than 1 in this case. Yeah, and that means, remember this picture, it will be here. It will be strongly coupled to the continuum of particle Hall excitations, and therefore it decays, strongly decays. So that means there is no zero sound as a well-defined excitation. It's a mess of the particle Hall pairs which doesn't have any sort of nice collective behavior. But this is all true, what I said, if the temperature is not low enough. If the temperature becomes very small, it turns out that the case of attractive interaction drastically changes from the case of repulsive interaction. And experimentally, it was observed in metals, of course. First, when the people discover, then lowering down the, if you go to liquid helium temperatures, a couple of kelvins, metals become superconducting. Yeah? And then if you measure, let's say, specific heat, it turns out there is no linear slope anymore, yeah, which I said is a feature of the Fermi surface. So, and then that was a remarkable discovery. So like a system of fermions starts behaving like a helium-4, yeah, which is bosonic system. Huh? And people start thinking, how could it be? And of course, the trivial answer, so trivial idea was the fermions combines in pairs. Yeah, and then the two fermions form a bound pair, they become a boson. And this boson can undergo superfluid transition like a helium-4. That was, of course, a nice idea. However, of course, this is a special case of metals. Two things becomes unclear. First of all, what is the attractive force that could generate these bound pairs of two fermions? Okay, people find out it could be phonon exchange. Phonon, yeah, this is a lattice vibration. They could generate an attraction between fermions in a very narrow region, which is width of the dBi frequency, the highest phonon frequency close to the Fermi surface. Okay, but this is typically not strong. There is attraction, but it's not strong. So one has to explain, actually, a thing, why this weak attraction can form a bound state. Because we all know, in 3 dimensions, the attraction, to form a bound state, you must have a relatively strong attraction. So there is a threshold phenomenon. Not every attraction leads to the bound state. Of course, for the metal, it was another issue. There is a Coulomb attraction that's repulsive. How could this weak electron-phonon interaction, attractive, dominates in some materials, not in every, in some materials over very strong repulsive Coulomb interaction and still leading to form of this bound state of two fermions. But the second question is a kind of more subtle, and it's really metallic side. We don't have in cold atoms, cold gases, we don't have Coulomb repulsion. Yeah? We could have attractive interaction, which can be controlled by the knob of the Feshbach resonance with the name Feshbach resonance. You can make it attractive, repulsive, strong, weak, whatever we want. But for the metals in the beginning, it was completely unclear how this weak electron-phonon interaction can generate the bound state. Yeah? People thought it's a bound state. It's actually not a bound state, but correlated state. And then comes Cooper, I think in '56, come with a brilliant idea how it could happen. And now let me tell you this Cooper problem. It turns out that the formation of these not bound but correlated states of two fermions, Fermi C plays an important role. And just to point it out, Cooper considered the following problem. Of course, this is very idealization of what's going on. So let's consider now the field Fermi C of n particles. And let's consider this to be frozen. Yeah? Field and frozen. This is my PF, Fermi momentum. Of course, in reality, I told you this is a gapless. Yeah? If this is a ground state, there is gapless excitation. You can freely move particles here and there. But let's consider it is frozen. You cannot move particles from there. As I say, it's kind of unphysical. Yeah, but let's think what the consequence could it be. And now let's consider two fermions, one here and one here. So here, let's say plus, and momentum P, and here minus, two components, yeah, with momentum minus P. Let's look or the solution of the Schrödinger equation for these two fermions is in the presence of the frozen Fermi C. What means frozen Fermi C? Means that for these two particles, only momenta larger than PF are available. The rest is simply out, frozen. So let's consider this hypothetical situation when the two particles move on top of the frozen Fermi C. Yeah? So of course, in this case, without interaction, for non-interacting, case, energy in this case, two particles, is larger or equal, okay, let's put equal to epsilon Fermi, right? They cannot have momentum lower than P Fermi, so therefore the energies cannot be lower than 2 epsilon Fermi, right? This is the result of the frozen Fermi C. For the non-interacting case, you will have it like this. Yeah? So let's now consider interacting particles and ask the question whether we can get the states of two fermions with the energy below this fermion. Yeah? That would mean we have a kind of bound state. Yeah? So whether in the interacting case, that would mean that you form a kind of bound state, right, in this very strange situation, yeah, where you cannot have, the particles cannot have momentum smaller than some PF. Yeah? So for this, of course, we have to solve the Schrödinger equation. minus h bar squared over 2m Laplacian for the first particles plus Laplacian for the second particles plus some interaction R1 minus R2 all acts on a two particles wave function. And this is our eigenenergy and the wave function. Yeah, that's what we have to solve. And specifically, we're looking for solutions with the energy less than 2 epsilon Fermi. Yeah, because I said without these things, it's 2 epsilon Fermi. Yeah? Of course, let's look in the most favorite case for forming a bound state on the center of mass momentum is 0. Yeah? So we write the wave function as a form 1 over square root of volume, sum over p, yeah, prime. Yeah, prime means yeah, and then some coefficient Cp, and here we have e to the I over h bar p R1 minus R2. Yeah, that's my wave function. I can always expand. 0 center of mass momentum, that's a very general form. Now I plug it in there, use the orthogonality of these things. So this can be transformed then in the following way. Now clear, here I will get 2 epsilon p, yeah, because each of this operator gives me p squared over 2m. Yeah, this epsilon p is always p squared over 2m. This is 2 kinetic energies, right? Then I will have plus, okay, let me put, okay, for the interaction, as usually the product in positional space, yeah, because I have to multiply this wave function with this in the momentum space, it goes to the convolution. And all equals E CP. That's exact the same equation in a momentum space. So this is in the momentum space. And CP, I forgot here. Yeah. Let me write down as a kind of 2 epsilon p better. Okay. So this is identical to this one, yeah, but now in momentum space. Of course, I cannot solve this, and Cooper also, nobody can solve this in general. So we have to make some assumption concerning this interaction. Yeah? And the assumption that was made by that time was mediated by this electron-phonon interaction for these ideas of the electron-phonon interaction. The assumption is the following. Let's assume that our V from P minus Q is minus modulus G, so it's attractive, when both epsilon P and epsilon Q larger than epsilon Fermi and smaller than epsilon Fermi plus omega 0 in this energy range. Where for simplicity, and of course at that time that was indeed for electron-phonon interaction indeed the case, but for simplicity of the formulas, let's assume that this omega 0 is much less than epsilon Fermi. Yeah, so it's just the Fermi surface, and only here you have this interaction, yeah, with omega 0 range, yeah, and 0 otherwise. So don't try to visualize this in a normal space. It's not anymore function of R1 minus R2. It's very strangely behavior, but this will allow us to solve this equation. Yeah? So it's sort of mediated by electron-phonon interaction, and we can solve this equation. Yeah? So you see, both has to be, yeah. So therefore, with these assumptions, we can perform the sum, yeah, easily. So here. So let me rearrange the things in a different way. What's the best way? Okay. So here we will have like this. 2 epsilon p minus e cp plus minus, yeah, because it's minus g over volume. And then you have sum over q belongs to m. Let me define m a bit later. And then cq equal 0. And this holds, okay. And here also p belongs to, we have it like this. And m is the following range. It is from pf up to pf square root 1 plus omega 0 over epsilon Fermi. So it's a momentum equivalence of this range. Yeah? So it's exactly the range of momenta where the energy belongs to this interval. Yeah? And for p outside this range, yeah, this is 0, and Cp is 0. So now this, of course, you can very easily translate it to the following thing, that Cp P belongs to this M, where you have non-zero. You just divide by this, yeah, this goes to the right, this you divide, and you get that it equals 1 over 2 epsilon P minus E modulus G, and here times 1 over volume, sum over Q belongs to M, CQ. How can we solve this equation? Similar equation we had for the zero sound. Huh? Absolutely similar equation. Yeah? So we have to sum over P, both sides, for P belongs to M. Yeah? But before, let me consider E. I'm looking for solutions. Let me write it simply as 2 epsilon Fermi. This is my lowest energy for the non-interacting particles, minus 2 delta. And if delta, if I find non-zero delta positive, that would mean that my energy, eigenenergy, exactly what I'm looking for, no? Below 2 epsilon Fermi. So with these notations, I can write it in the following way. I can write Cp, maybe just better to rewrite first, 1 over psi p plus delta, and here I have 1/2 modulus G divided by 2, 1 over volume, sum over Q belongs to M, this CQ, where I introduce, it's a very standard notation, psi p is epsilon p minus epsilon p minus epsilon Fermi. We will use this notation today very often. Yeah? So now what I do, I sum over 1 over volume, sum over P belongs to M, both sides of this equation. Yeah? Then you have sum on the left, sum on the right, and some of these things on the right. And these sums I just cancel. No? The same trick we did for the zero sound. So what you end up with is 1 equals modulus G over 2, 1 over volume, sorry, this was, yes, no, 1 over volume, sum over P belonging to M, 1 over psi P plus delta. That's the equation you have to solve. And of course, what we do, we just replace summation with the integral, modulus G over 2, integral dP, yeah, such that P belongs to M. And now 2 pi h bar cube, 1 over psi P plus delta. It's all finite limit, so we can easily calculate the integral. This is the integral over direction, 2 pi h bar cube that comes out, and then you have integral also only the radial one. It's a p squared divided by psi P plus delta, and here we integrate from pf to pf square root 1 plus omega 0 divided by epsilon Fermi. Of course, you can calculate this integral exactly, but we can use the fact that omega 0 is much less than epsilon Fermi, so actually the upper limit is not much different from the lower limit. Yeah? So actually you integrate over the small area near the Fermi surface, yeah? And therefore for our purpose would be, so we write it p squared dp. Yeah? I remember this definition of psi p. It is p times m d psi p. Yeah? And because I am integrating over small area near the Fermi surface, I can replace it with p Fermi m d psi p. Yeah? This is, of course, here comes the already approximation, but you can check that it's a good one just by making this integral exactly. Yeah? So what you get here would be the following. It would be modulus G divided by 2. Then we have this m p Fermi over 2 pi squared h bar cube. Yeah? And this is exactly density of states at the Fermi surface. Yeah? And then the integral that we have to calculate is from d psi. Yeah, I skip now p, because it does matter. Psi plus delta. And psi ranges from 0, yeah, because when p equals p Fermi, psi p is 0, because it's minus epsilon Fermi, to omega 0. And this is this now is exactly, this is density of state times G, gives me F divided by 2. Yeah? And the integral is log delta plus omega 0 divided by delta. Yeah? And again, yes, so, and then you would looking for the case, of course, we have a weak interaction. We want to have weak interaction that we typically will have, and you will see that from the answer. The delta is much smaller than omega 0. So you can even further simplify this. Of course, it's no need. I just can solve it explicitly. Yes, but I would write it like this. F over 2 log delta omega 0, over delta. Again, approximately. And now you see that this equation always has a solution, no matter how small f is. Yeah? You always get a solution. Delta is omega 0 e to the minus 2 over f. You always have a solution. Doesn't matter how weak f is. Yeah? And indeed, we see that f is small, delta is exponentially smaller than omega 0. So this is fine. This approximation. But the solution always exists. So in this case, no matter how weak is the interparticle interaction, you always find a kind of bound state solutions with the energy which is less than 2 epsilon Fermi. The lowest energy is continuum threshold. Yeah? So, but you could, so we actually solve, at least pretend to solve the problem. How could weak interaction generate result into the bound state, or correlated state, better say in this case. But you may ask me, well, but you did a very tough approximation here. Is this a reason for this or not? Let's just consider now no frozen Fermi C and the same type of approximation for the potential. Yeah? So let me now have here no frozen Fermi C. Yeah? Let's just check that the same model for the potential will result into the threshold for the bound state. Yeah? Then it would be honest. Yeah? Without the Fermi surface, two particles in vacuum form a bound state if the interaction is stronger than something, that means a threshold, but in the presence of the Fermi C, no matter how weak is the interaction, it always results into the kind of bound state. So let's check it. No frozen C, no frozen Fermi C means that I have to put epsilon Fermi to 0. Yeah, I just put it to 0. So, and therefore, my M, area M in this case, reduces from 0 to, and now I will have PF square root of 2m omega 0. That would be my M, yes?
I do understand why you are not going to see the epsilon f goes to 0.
Because epsilon Fermi is just this upper bound for the frozen part. I just want to remove this frozen part. I just want to use my formula again. Utilize my formula, but how can I do so? Here, all these states were frozen. Yeah, these particles cannot allow going here, and this also not going out. So now I want to reduce this frozen part to 0, no frozen part, and I can achieve it in my formulas by simply putting PF to 0. Yeah? Yeah. So then I just simply, you can go through all this what I have here. Yeah. You, like this is true, so the M is different, then you go here, then you go, and the only thing where you have to be careful, started in, actually, psi p is epsilon p, so the equation that I will have in this case would be like this. Modulus G over 2, and then I will have integral dp over m, let's say 0, let me call it 0 to distinguish, 2 pi h bar cube, and then I will have 1 over epsilon p plus delta. Yeah, because epsilon Fermi is 0, psi p is epsilon p. Yeah, I just put everywhere epsilon Fermi to 0, and this equation reduces to this one. Yeah? Is it clear? So now I just continue. 4 pi, 2 pi h bar squared, integral dp p squared from now 0 to square root of 2m omega 0. Yeah? 1 over p squared over 2m plus delta. So the integral I have to calculate. So now let me write it like this. G m divided by 2 pi squared h bar cube. And then we have integral 0 square root of 2m omega 0 dp p squared divided by p squared plus 2m delta. Now just put 2m from there. And now it is, let me keep the prefactor the same just to save time. So here, 0, 2m omega 0 dp, 1 minus 2m delta divided by p squared plus 2m delta. Yeah, clear what I did. Yeah, I add and subtract here 2m delta. Now when I add, it's just 1. Then I subtracted this term. And now I can perform my integration. G m 2 pi squared h bar cube. And here, first term gives me square root of 2m omega 0. Yeah, and then second one, we have this arctangent. Yeah, and we have square root of 2m delta, arctangent of it is square root of omega 0 divided by delta. So now again, it is natural to assume that delta is much smaller than omega 0. We're just looking for the weakly bound state here. So therefore, here stays arctangent of a very large number. Yeah, that is pi over 2. Yeah, when arctangent very close to pi over 2. So what you have here is G m 2 pi h bar cube. Then we have, okay, let me take these things out. I will have square root of 2m omega 0. And I will have 1 minus, here I will have square root of delta over omega 0 times approximately pi over 2. Yeah, so I replace arctangent pi over 2 for omega 0 over delta much larger than 1. And now you see that the solution exists. So there is a threshold for the solution, yeah? Because it all equals to 1. Yeah? If G is small, yeah, this thing is less than 1. When delta is 0, it is 1. Otherwise, it is smaller than 1. So you cannot have the solution when G is small. Yeah? So you see, the solution starts for, there is a threshold when m square root of 2m omega 0 divided by 2 pi h bar, 2 pi squared h bar cube modulus G is larger or equal than 1. So indeed, we recover known results from quantum mechanics. Yeah? So if you have attractive interaction between two particles in vacuum, bound state exists only when the interaction is strong enough. Yeah? So it is G and omega 0, that's the kind of combination what you have to achieve. And this has to be larger than 1. Only then you have a solution for delta. Yeah? So that's okay. Then our model was not so stupid. Huh? So at least it reproduces the known results. Maybe not up to whatever, but it reproduces the result that in 3D you must have a threshold to form a bound state. But if you add a frozen Fermi C, always, no matter how weak is the attractive interaction, it forms this state with the energy less than, so you form a bound state in this case. Yeah? So particles cannot move separately. They form, and actually you will see that in this case, it is, gives almost correct exponent. Yeah? So you can modify a bit this original Cooper problem to say, okay, I have two excitations around the Fermi surface. Yeah? So here there are particle excitations, here there are Hall excitations. Yeah? So I just remove the constraint of the frozen Fermi surface, so I can let talk not about the particles, but talk about excitations. But it can be particles and Hall-like, and the price would be, or the result of this would be, you just replace 2 with 1. And that is correct exponent for BCS. This is correct exponent for BCS. At the moment, we just take only half of the possible states for rescattering of these two particles. So they just collide, they go to another state, another state, another state. So momenta always opposite, yeah, because the total momenta is 0 and conserved, but they cannot go below, yeah? They stay only on top, above. If you allow to go below, then you will have -1 over f. Yeah? So now this was a nice guiding principle for what's going on. So let me now try to modify accordingly, taking into account this effect, modify our Hamiltonian for the interacting Fermi systems to take this effect into account and see what happens in this case. So we're now going to arrive to this BCS type of Hamiltonian. So you see, this BCS is essentially collective phenomenon. You need many particles to exclude large part of the states from your scattering process. As we know, inside the Fermi sea, it's all blocked. Particles cannot scatter in this state. So they stay only close to the Fermi surface. And this is essential for forming these type of states. Without Fermi sea, yeah, there would be no BCS. Or you have to go to very strong attraction, then you form really bound states, and then you should talk about molecules rather than these Cooper pairs. So let me now come back to the Hamiltonian. So what we have is this prime means minus mu n. Yeah? It's sum over p and sigma epsilon. Okay, let me write here psi p. And I remind you again, psi p from now on always like this. Yeah? Standard definition. And then you have AP sigma, A dagger, AP sigma. So I will write two forms such as to explain you what is the meaning of, it would be easier to, so okay, minus, okay, plus G, which is negative, plus G over volume. Probably, let me write first this one. dr, psi dagger plus R, psi dagger minus R, psi minus R, psi plus R. Yeah, that was this form, remember? Or I used the following thing, so this is unchanged, and now I write it in this form. P1, PQ, P2, and Q. And now we have this A, P1 plus Q plus component, dagger A, P2 minus Q minus component, dagger A, P2 minus A, P1 plus. That was two forms of the same Hamiltonian. Yeah? So now how can we take into account this form of these Cooper pairs, these correlated states of particles with the opposite momenta? Yeah, because there are many states, at a continuum of such states. Yeah? Total momenta 0, but the P can be whatever. Yeah? So in this case, you would think in terms of a kind of mean field that formed by these two particles added. Yeah? So you have many such states like a BC, yeah? For these pairs with 0 momentum. Yeah? And that means on this level, yeah, I just once replace, I can introduce this delta, which is G times the average of this field. Let's assume it is non-zero. Yeah? Two fermionic fields, it's a kind of bosonic operator, so nothing prevents bosonic operator to form an average value. Yeah? With fermionic operator you have a problem, but with bosonic not. It can form a bound state. Yeah? So if I write it in a momentum space, assuming that I have translation invariance, so I don't want to have a, so this is sort of kind of ground state, which I have to find out. Yeah? Because this, of course, for Fermi C, this is strictly 0. Yeah? But we want to have a condensate of these P minus P pairs such that these shouldn't be 0. Right? like if you have a condensate, average of your A dagger and A becomes non-zero. Yeah? So it's a similar story, but now we have quadratic operating fermions. So if I write it in a momentum space, it gives me sum over P average of A minus P minus A P plus. So here I use translation variance. So that means if I remove particles with a total zero momentum, P minus P. Yeah, it's exactly this kind of things that yeah, not with something else. So now see what happens. So in this case, what you would get, let me write only this part. Yeah, and of course I will have delta star, which is G psi plus dagger R psi minus dagger R. Yeah. So by doing this replacement, I will get for this part only, I would write this as an integral dr. And here I will have delta star psi minus dagger R psi plus dagger R plus psi plus dagger R psi minus dagger R times delta. Of course, to be honest, I have to subtract also minus delta modulo square divided by G, but this is a constant. It's important when you start calculating the absolute value of the energy, but it doesn't contain operators anymore. Yeah? So I decouple these four fermionic operator in terms of mean field times a pair of fermionic operators. Now this is the trick that makes it possible to solve the model at the end, because quadratic Hamiltonian we know how to solve. Huh? So therefore, this is in this form, but now let's see what happens here. This is also instructive to see, and then you will get what is called Bcs Hamiltonian. But what is it on this level? Yeah? So on this level, I should either replace this pair with the average value or this pair with the average value, yeah? Because this pair would correspond to this delta, yeah? And this one would correspond to this term, yeah? But when I do it, yeah, you see, P minus P means Q equals 0, yeah? That means, and this is a rigorous statement, in the BCS Hamiltonian, you consider only scattering between particles with the opposite momenta. Yeah? So that means if I write this term with Q equals 0, I just throw them away, these collisions which change the momentum. Only those particles, plus and minus, its total momentum is 0, collide. The rest I just ignore. This is BCS model. Yeah? Because then you see, then if I forget here Q, I have independent summation over P1 and independent summation over P2. And this is exactly the reason why these, so what we will have here. So in this form, it go into the delta times sum over P. And okay, let me write it maybe. Okay, let me write now finally what comes the BCS. I think it would be better. I write the two form of the BCS Hamiltonian rather than have all these pieces. So here we will have one case where we start with is sum over P and sigma, psi P, A P sigma dagger A P sigma, plus integral dr, and then we have delta star psi minus r psi plus r plus delta times psi plus dagger r and psi minus dagger r. That's one form. Or you write it, this term doesn't change. And here you get plus sum 1 over volume. No, sorry, without it. It was absorbed into, yeah. Sum over P. And now you have, these terms gives you delta star, A minus P minus AP plus delta, AP plus dagger, A minus P minus dagger. This is what is called BCS, Bardeen-Cooper-Schrieffer Hamiltonian. Yeah? This is BCS. BCS Hamiltonian. It takes into account, as I said, it's a model. Yeah? It takes into account only collisions between particles with the opposite momentum. If they don't have total momenta 0, this pair does not collide. This is, of course, approximation, and we will see, I will tell you, that it actually reduces, you get the, in a real gas, where these collisions, of course, exist. And this will modify, let's say, critical temperature, some quantities, but essential part, the exponential part, this sort of behavior, this model tracks exactly. This factor depends, and I will explain you why, on all these collisions that we neglect here, and this has to be taken into account in the end if you want really go to experimentalists and say, okay, you have this gas, that temperature you need to achieve in order to see BCS. Yeah? So now what we are doing, now let's look at this Hamiltonian. We were trying to solve it. Yeah? Of course, you can try to solve it in the most generality, but what we can simplify things, of course, you see, so here, it's a complex number in general. Huh? But on the other hand, this is gauge variant terms. Yeah? I can absorb the phases of these things if they're constant. And of course, in a ground state, we assume special homogeneity. So there is no reason for them to depend on position and time. The constant phases from here, you can absorb in redefining your operators. Yeah? Because it's gauge variant both terms. So therefore, we assume that delta star is delta. Again, we're looking for the ground state. These fluctuations of this delta would generate you what is called collective mode Bogolyubov-Anderson sound. But it's not the part of this story. So, and we want, of course, to diagonalize it. Yeah? Remember, we did it already with this part. Yeah? Remember when I introduced particle-Hall excitations, it was exactly diagonalizing this part, going from particles operator to the excitation operator. Yeah? So now we want to do exactly the same story. So that means that we want to write HBCS in the form of some ground state energy plus excitations. Sum over P and sigma, EP, as you will see that sigma will not depend on sigma, alpha P sigma dagger alpha P sigma. Remember this, free Fermi gas. So we want to find, in general, of course, what are these operators in terms of the initial A and A dagger, what are the excitation energies, yeah? And we can also calculate these things, and if we know these operators, we can define the new ground state. Like a new ground state, it is something that is annihilated by all this excitation operator. That's our new ground state. And we know everything, yeah? Because it's quadratic theory. We know everything. Yeah? So and this can be achieved, this diagonalization is, of course, this we already know. We have to use this Bogolyubov transformation for this case. Similar to what we had before for the ideal Fermi gas, to diagonalize it and to go to particles, to the excitations with positive excitation energy. Yeah? So this we do with Bogoliubov transformation. So we have our alpha p sigma. Let me write plus. Yeah? That would be slightly different, but I will write the general formula. Remember what we have for the ideal Fermi gas. Yeah? We have here UP, AP plus, and then we have plus VP, A dagger minus P, and I put here minus. Yeah? Remember, without plus or minus, that's exactly what we have for the ideal gas, and this was a step functions, yeah? That was above P Fermi 1 and 0 inside, and it was inside 1 and outside 0. Yeah? So similar expression. And again, the same reason why I put here minus P, yeah? Because I want this excitation corresponds to a particular fixed momentum, yeah? And this remove excitations with momentum P, and I remove momentum P in two ways. Either I remove a particle with momentum P, or I add a particle with momentum minus P. In both cases, I reduce. With plus or minus, you can think in terms of electron, projection of a spin of some axis, and then it's the same story. Removing projection, you can either remove particle with this projection or add a particle with the opposite one. Yeah? And after some experience, and sort of trial and fail experience, for the minus, you should write here minus. So a general formula, let me write like this. Alpha P sigma is UP AP sigma plus sigma, yeah, plus or minus, VP A dagger minus P minus sigma. That's kind of things. And of course, the dagger operator looks exactly the same. Yeah, just take a dagger. And of course, I can put UP and VP complex, but I will not. Yeah? Because it will be sufficient for the ground state. They are real. Yeah? So that means UP star is UP, and VP star is VP. You can try to play with the complex one and see what happens. Yeah, and but you will see that there would be, at some point I will tell you what will be different, but you can continue with the real ones. Yeah? And of course, what I have to do, first of all, I have to take care about the statistics of these excitations. Yeah? And statistics, because I made them from two fermionic operators, I want them to be fermion, right? I want that alpha P1 sigma 1 and alpha P2 sigma 2 anti-commute to delta sigma 1 sigma 2 and delta P1 P2. The rest, alpha alpha is, and alpha dagger should be 0. Yeah? That's what I want to have, because U's and V's here at the moment, they are sort of not defined. Yeah? There is a lot of freedom in choosing them. You can check that this is automatically fulfilled with this choice when they are real. Yeah? You can check it. Yeah, with this choice, it's automatically fulfilled. This is a less trivial thing, but let me do it. It's not complicated. Yeah? And then we get the general conditions, what you would have, what you need to impose on U and V to have to these new operators to be fermions. It's very similar to if you know this Bogoliubov transformation for bosons, then you want the commutator to be 1, and so that they are bosons. So here we want to have fermions. Yeah, so let me now calculate this alpha P1 sigma 1 with alpha dagger P2 sigma 2. Yeah, so what it is, I have a, so here I just plug in UP1 AP1 sigma 1 plus sigma 1 VP1A minus P1 minus sigma 1 dagger. And I have to anti-commute with UP2, and I have A dagger P2 sigma 2 plus sigma 2 VP2 A minus P2 minus sigma 2. I just plug in my definitions in there. And then I have 4 terms, but I know that the only non-trivial ones when I have here A and here A dagger, so this one and this one. Yeah? Because A with A anti-commute, A dagger with A dagger anti-commute, yeah? So I just have 2 contributions. I have UP1 and UP2 and anti-commutator AP1 sigma 1 with A dagger P2 sigma 2. And I have the second term plus S sigma 1 sigma 2. And then I have VP1 VP2. And I have anti-commutator A minus P1 minus sigma 1 dagger with A minus P2 minus sigma 2. Yeah? And these anti-commutator are just deltas. Yeah? So both of them are delta P1, P2, and delta sigma 1, sigma 2. Yeah? Because if minus sigma 1 equals to minus sigma 2, sigma 1 is equal to sigma 2. Yeah? So what I get here is sigma 1, sigma, so I get UP, let's say 1 squared, sigma 1 times sigma 1 squared, always 1, plus VP1 squared, delta P1, P2, delta sigma 1, sigma 2. And I want, if it is, you see that this has to be 1. This is condition. Then if this is fulfilled, my new operators are fermions. Because as I checked, as I said, this would be automatically fulfilled. Yeah? So therefore, this transformation defines for me the transformation from one fermionic operators, to A and I dagger, to another pair of fermionic operator, alpha and alpha dagger. But this requires these conditions that alpha p, well, in a general case, you will find out this one. In our case, we consider them real, so we get it like this. Remember, for our ideal Fermi gas, we have UP was step function PF minus P, and VP was again the step function P minus PF. It's fulfilled, yeah, because we have 1 everywhere. Yeah? But it's in general, you have it like this. Yeah? So good. So now we know we have one constraint to our U's and V's. Yeah, so, but this constraint immediately tells you, yes. So what is the strategy? The strategy now can be twofold. I don't know which one you prefer. The possible strategy is to make inverse. Yeah? Because our Hamiltonian is given in terms of A. Yeah? So we take inverse, we express A in terms of alpha, put it in this Hamiltonian, and ask that it has this form. No alpha, alpha, and alpha dagger, alpha dagger. Yeah? That's one strategy. Second strategy is using what is called equation of motion. If you have operator of that type, yeah, if you take the commutator, yeah, let's say with alpha p sigma, commutator, yeah, what you should get? Exactly. You should get minus EP alpha p sigma. Yeah? This is what you should get. This alpha is given here in terms of A and A dagger. You just calculate this commutator, and once that what stays on the right is proportional to, again, alpha p sigma. That's another way. Yeah? So which one is better, you decide for yourself. It's actually a very good exercise, but I will tell you the easiest way to find the inverse. Yeah? This should remind you the very famous trigonometric identity. Yeah? Cosine squared plus sine squared is 1. Yeah? So for the fermions, this transformation, unitary transformation, corresponds to rotation. Yeah? For the bosons, you would have here minus, and that's hyperbolic rotation. But for fermions, it's a compact group. It's really rotation, so it's a compact group. So to find inverse, we have to do inverse rotation, right? So this looks like UP equals some cosinus, it's too many O's, cosinus phi p, and VP is just the sinus phi p, right? And it looks like indeed like rotation. Yeah? So what we want to do, we just go rotation, inverse rotation with phi to minus phi. That means u's remains u's and v goes to minus v. So inverse transformation looks like AP sigma is UP alpha p sigma minus sigma VP alpha dagger minus p minus sigma, and AP dagger sigma is UP alpha dagger p sigma minus sigma VP alpha minus p minus sigma. That's the inverse transformation. You can check. Yeah, put in here, put this one, and see that because of these things, you get the same. You get AP sigma. Yeah, you can check. These you can easily check. Yeah. So now the strategy, we put these things into here. Yeah, enjoy some algebra. Yeah, so here would be a lot of terms. And we plug it in here, and then we ask that no alpha and alpha dagger terms. We want that those are absent. Yeah? Then the only thing we have is this one, but this is what we want to have. Huh? Of course, you will also get the term alpha dagger. Yeah? But this we know how to treat. Just take anti-commutator. Gives you some constant ends up in here. Yeah? The rest comes in this form. Yeah? So I will not do this exercise. Those who want to see details can come and I will explain. But the conditions that you get is the following. Took psi p, UP times VP has to be equal delta times UP squared minus VP squared. This is what you get. And I remind you, we have this condition. Two variables, two conditions, those has to be defined. Yeah, up to plus minus, but yeah. If you do what I said in this way, yeah, then you get what is called Bogolyubov-Dagen equation. And this way you should follow when you do these things in, let's say, in the harmonic trap. Yeah, when you have time-dependent, position-dependent potentials. Then equations look like this. EP times UP. IP, I didn't define it at a second. Equals, so this actually Yeah, it's this one. Huh? You get this set of equations. This is two equivalent approaches. So now the solution. So you can either combination of this and this, or from here, it doesn't matter. Yeah. In the end, you should get the same. Of course, to select the right solution, okay, let me write it and then I tell. Because here it's squares, yeah? And so in the end, you have to choose the right plus or minus, yeah? And of course, choose right plus or minus helps you these things, yeah? When delta goes to 0, we should recover this form, yeah? Because delta 0, this term disappears, and we have just our ideal Fermi gas where they know the answer. Yeah? This helps you to choose the proper sign in your solutions. So now what we get is following. EP is square root of psi p squared plus delta squared. This is the energy of our excitations. And then we have UP squared is 1/2 1 plus psi p divided by EP. And Vp squared is 1/2 1 minus psi p divided by EP. These are the solutions. You can check. Just plug it in, see that it satisfies both of these equations. Huh? So what we see from here, let's first look at these things. If delta is non-zero, again, if, yeah, because we say there is this average, non-zero, yeah, so the next step we have to really write the equation on this delta, and indeed to be sure that there is non-trivial solution, delta non-zero, yeah, because delta 0 is just a free Fermi gas. It's not interesting here. Yeah, so, but if delta is non-zero, you see how the spectrum looks like. It's completely different spectrum compared to normal Fermi gas. Just remind you, this is excitation energy. That was P Fermi, and that was EP. In the ideal Fermi gas, we have it like this. Yeah? So now, of course, delta, you will see, would be much smaller than epsilon Fermi, and it modifies only here, right? Because if I far away from when psi 0, away from this point, this dominates, and you get modulus psi p, this is this curve, and only close, so you get this form. And this is delta. So you open the gap. So this now, with this, your single particle excitations become gapped. So remember I gave you the picture of the Fermi surface, like a water, yeah? So you just slightly blow and then you see the waves. It was gapless. So now this water is frozen. There is a very thin layer of ice covering the water. So therefore, if you just, nothing happens with the single particle excitations, yeah? They remain correlated, P minus P remains correlated, and to break these correlations, you need some energy. Of course, if you hit, the ice will be broken, yeah? But if you're gentle, well, it remains the same. So you cannot create for free single particle excitation here when you have, in the case of a normal Fermi gas or Fermi liquid, because this was a feature even in the repulsive, not only ideal Fermi gas, but also repulsive Fermi liquid, interacting one. Yeah? So gapless excitation. Now they become gapped, yeah, and this means actually what is called, this is exactly the reason for superfluidity in fermionic system. So how these UPs and VPs look like, let me now erase probably, I don't know what's better to erase. Okay, I guess I can. No, these are probably neat. Let me erase this one. So UP squared and VP squared, and this is P, and this is P Fermi. At P Fermi, you see these terms are 0, so you just have 1/2. Yeah? Let's here 1. So here 1/2. So one of them goes like this. It's a smooth functions, as you can see, and another goes like this, such that the sum is 0. Yeah? And this is VP squared, yeah, because when you are inside, below the Fermi surface, this is negative. Yeah? And UP squared is here. So what is the meaning of these things physically? Let me now calculate what's the distribution would be, assuming that I'm in a ground state, which is annihilated by all this excitation operator. And if you want from here, the ground state, I can immediately write you how it looks like. Afterwards, let me now calculate. Assuming that we have it like this, what is the particle distribution? Particle distribution. Let's say for one of the component. What is this? Yeah? For this, I have to plug in these expressions. Yeah? So what I will have ground state, and now I'll have UP alpha P sigma delta minus sigma VP alpha minus P minus sigma. And now I will have UP alpha P sigma minus sigma VP alpha dega minus P minus sigma, and now ground state. Yeah? But ground state satisfies this condition, so therefore this term, you see, here alpha acting on the ground state gives you 0. Yeah? Because here I have in this term, I have alpha acting on the ground state, and this is 0. For the same reason, this term acting here, because this condition also is equivalent to this one as a conjugate, this term also disappears. Yeah? So what I will have, minus sigma gives me 1. I would have ground state. So VP squared, ground state, alpha minus P minus sigma, alpha dega minus P minus sigma, ground state. No? But now I use the anti-commutation relation and writing this as 1 minus alpha minus P dega minus sigma, alpha minus P minus sigma. And this part, again, acts on the ground state and gives me 0. Yeah? You see? And this term, alpha, acts on the ground state. And the ground state, there is no alpha part, no excitations. It's a ground state. Yeah? So therefore, this term disappears. And what I get VP squared. So this is now a distribution of particles in this ground state. This one. It's a continuous. no discontinuity, like what we have in a normal gas, repulsive gas, or liquid, Fermi liquid. It's now continuous. So like kind of temperature, yeah, like at a finer temperature, it also makes it continuous. The temperature here is 0, but you still have this behavior. So what is this ground state? Yeah, you can solve this and find it explicitly. So that is the answer. You have to sum over all P, UP plus VP, A dega minus P minus sigma, A dega P sigma, acting on the vacuum. This is the solution for the ground state that is annihilated by these operators. And you see how it looks like. Yeah, you have a vacuum state, and you take a P, yeah, that means momentum P, and you have plus and minus particles. And this is amplitude to have it empty. This is the amplitude to fit the pair, P and minus P, with the opposite type. Yeah? So you populate this in pairs. Yeah, which is called in Cooper pairs or whatever. Yeah? So in case we are here, yeah, delta is 0, you see that you get a really field Fermi C, yeah? Field Fermi surface, because this thing is 0 outside. Yeah? So for P larger than P Fermi, you don't populate at all use 1. Yeah? And for P below P Fermi, this one is 0 and this is 1. You populate all the states inside. Yeah? So you see this is wave function sort of continuously change you, well, not continuous, because it's already this one that's non-zero. So goes from this solution is for free Fermi gas and this exotic ground state. Yeah? So of course it's all very nice if delta is non-zero. Yeah? So now we have to find out what is this one. Yeah? What is this equation? Yeah. So you can also see probably, okay. Let me now come back to the gap equation. Or at least to start with, because I will need some, I'm not sure that I will finish all the technical details today, but next lecture we finish them. So gap equation. As you guess, it's equation for the delta. So we have delta here. And we have it there. And let me derive this gap equation for finite temperature, even for finite temperature. Zero temperature limit is trivial, right? In a finite at finite temperature, what happens, you have a Fermi-Dirac distribution Yeah, these are just free fermionic excitations, right? So they are just populated according to Fermi-Dirac statistics. Yeah? At T0, because EP is always positive, so for 0T you have 0, yeah, is what we used, yeah, to find out what's the particle distribution number at T0. But at finite temperature, you can generalize the equation I derived for you for T0, like a particle distribution number, take into account that this is now also non-zero. Yeah? So let me now go back to this equation and just continue. I will have G over V. I do exactly the same thing like I did when I derived the particle distribution number. So I have my my definition of particles operator, right? From here. So here I will have two terms. I will have UP alpha minus P minus sigma plus minus sigma VP alpha dagger P sigma. That's one thing. Yes. And now we have UP alpha P sigma minus sigma VP alpha dagger minus P minus sigma. Yep. Yeah. Okay. So now I just have to expand. And it's clear the things that I have this alpha and alpha dagger, alpha alpha, I cannot be orthogonal. Yeah? So I only have to keep terms with alpha and alpha dagger. Yeah? Because I start, if it's, let's say, alpha dagger and alpha dagger term, I start with some states. So here's the density matrix. Yeah? So there's some state with some occupation of quasi-particles, non-zero. And I add two of them, two extra, and it cannot be the same state. Yeah? So the only things that therefore I have is this term with this one and this one with this one. Yeah? And in both cases, you see I get UPVP. Yeah? And minus sigma. I have minus sigma. Sorry. Because here minus sigma, yeah, I have to switch the sign of sigma. So here, right? Because if it's minus sigma, here would be plus. Yes. Does it make my life easier? Probably. Somehow I don't see. Okay, let's continue. Let's see. Then we will have, both cases will have UPVP. And then we will have two averages. One is this one, minus sigma alpha minus P minus sigma alpha dagger minus P minus sigma. And then we have this one, which is plus sigma. And then we have alpha P sigma dagger alpha P sigma. Somehow, let me check. I don't like this sigma. Actually, why do I write in these sigmas? God, sorry. Just definition was right in front of me, minus plus. So it was, sorry. So that means that here I have plus, here I have minus, and here I have minus again, plus, and here I have minus, I have plus. So I have minus sigma minus, and I have minus. Here I have plus. Yeah. And here I have. Yeah. So it's like this. So, and this here, we do exactly the same trick because we know this is a number operator. Yeah? So here I write these things as 1 minus alpha minus P minus dagger alpha minus P minus. Yeah? And then finally what I get, let me take minus out, because minus 1, okay, minus G over volume, and then I have sum over P, UPVP, and here I will have 1 minus this operator, and this is NP minus, and this one minus NP plus, this excitation, which is exactly this one. Yeah? So finally, if I just, they are the same, they're independent on plus and minus. So finally, I can just combine the two, and we are almost there. So what we get, delta equals minus G, gives me modulus G, right? Because minus G is just modulus G, I know that G is negative, divided by volume. And here I have sum over P, UP, VP, 1 minus 2 e to the EP over T plus 1. Or I can continue these things and combine. So I write it, so this, let me take this bracket, yeah, is e to the EP over T plus 1, and I combine the two, get e to the EP over T minus 1. Yeah? If I take EP over 2T out in both cases, yeah, I cancel it, so here I will get in total tangents hyperbolic of EP over 2T. Yeah, because I get here e to the P minus e to the minus EP over 2T, and here I will get, so this is sinus hyperbolic, this is cosinus, in total get tangent hyperbolic. So finally you get here modulus G divided by volume, sum over P, UP VP, tangent of EP over 2T. And finally, I have to walk a bit about this product, UP and VP. Yeah, and I have it here. Yeah. So let me form a product UP squared times VP squared. Yeah, from here. So what I get here, I will get, if I combine things, I will get 1/4, yeah, prefactor. I will have EP squared in denominator, yeah, because here we'll have EP and here EP. But then I have here product of EP plus xi, EP minus xi. So A minus B times A plus B, so it's squares. So it gives me EP squared minus xi P squared. Yeah, and if I now remember my definition of EP squared, yeah, so I get here 1/4 delta squared divided by EP squared. So now I can easily extract the square root, yeah, because it's full square. So finally, gap equation we have to solve is like this. Modulus G divided by volume, sum over P, and then we have 1/2. Yeah. So I have delta, let me write it like this. Delta times, and now I have tangent hyperbolic EP divided by 2T, all divided by 2EP. Of course, we have two options, delta 0, but then make no sense. We have ideal Fermi gas, or delta is non-zero, and I cancel both sides. Yeah? Delta 0 is always solution. So I cancel delta on both sides. And this is my gap equation. This solution I have to solve to find delta, which comes in here in a kind of non-trivial way. Tomorrow we come back to this, and I will show you how to eliminate. If you look carefully at this equation, yeah, if you look carefully at large momenta, because here is the sum of all momenta, And if I look at momenta, very large momenta, let's say infinity, because in principle I have to sum up over all momenta here, that's what is Cooper channel, the two particles Cooperon. Remember this of Eric lecture. The two particles come in the same direction, rescatter, 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 and in between they can scatter to infinite momenta state and come back, etc. etc. If you look at large momenta, this one, because EP goes like p squared over 2m, because large momenta psi becomes very large. So tangent is 1 hyperbolic. So here you have a sum over p m over p squared. This sort of contribution of large momenta. This is divergent one. So I will show you how to get rid of this divergence, and formulate things in terms of scattering length. This divergence comes from our model for the interaction, contact interaction, short-range interaction. Again, when you go to very large momenta, you have to take into account the structure of your interaction. You cannot say anymore that it's point-like. This is a point here with momentum. Momentum are limited. It's a fine approximation. If momentum becomes very large, eventually this structure, inner structure of the interaction comes into the play. And I will show you how to get rid of this. How to make finally nice expression that you can put on compute or solve analytically in some limit, etc. So I stop now. Questions? Sorry? Well, in fact, you're right. So delta, I have to, the delta should be momentum dependent, of course, but again, this momentum dependence comes from very large momenta. And the whole idea is, because again, we're interested in physics near the Fermi surface, and somehow we have to remove this high momentum. And high momentum here, it's when two particles collide at a very high momentum. That means they come close to each other. So this actually means that P is much larger than P Fermi. They come close to each other, and therefore it's two-body problem. When they come close to each other, they don't care whether they are just two particles in the universe, and they collide according to the Schrödinger equation, or they are in the many-body systems. And that's coming back to the Schrödinger equation that will help. I will show you tomorrow how it works. Okay. So you see, this is intrinsically many-body effect. Fermi surface plays a very important role. Without it, there is no BCS. You can have, of course, a bound states if the interaction is strong enough, but no BCS. Okay. If there is no more questions, yes?
What's the physical significance of that gap in that flow?
Gap?
That gap, I mean.
It's exactly actually at some point was mentioned in the first lecture by Mikhail. It really makes a gap if you shine the photons, electromagnetic field, if the energy does not exceed, or the photon does not exceed 2 delta, because it has to break the pair. Delta is the energy per particle. To break this correlated state, you need 2 delta. If the frequency does not exceed these 2 delta, the material is transparent. It's really the minimum energy that you have to put into the system to create excitations. If no more questions, we have a lunch.